In this video, we will show how to design a girder beam using an Excel file to consider and summarize the information presented in the previous video for practical applications. This video is strictly showing how to organize the data in Excel spreadsheet format for quick evaluation and design of the plate girder. If you want the detailed calculations behind, please refer to the previous videos about plate girders by clicking the link in the top corner or in the description below. Let us start by defining our example problem, where we have a 48-foot long plate girder, and lateral beams rest on the girder at 12 feet offset of each other and from the end supports of the girder. These create concentrated combined ultimate loads of 60 kips. This also creates a lateral support that will prevent rotation of the top flange of the girder at these points. The end supports are treated as simply supported. Under each concentrated load is a pair of bearing stiffeners. Double bearing stiffener pairs are placed at the supports. The plate girder is made of 16 by 1 inch top and bottom flanges and a 63 by 3/8 inch web. The stiffeners are 7.8 inch wide and 3/4 inch thick. All plates used are of A36 steel. We can create a finite element model of the beam with the pin support at one end and a roller support at the other. The units in the model are in inches, and thus we add a uniform load for the factored combined load that includes the weight of the girder as 0.5 kips per inch. We can define the section of the beam as follows. Note, however, that if all is needed from the analysis are the bending moment values and shear along the girder, it is not necessary to include this step because we have simply supported condition. This is a statically determinate problem, and the moments and shear will not depend on the stiffness of the elements. For more information about this and beam analysis in general, please check the video in the top corner. After running the analysis, we obtain the following shear diagram and the following bending moment diagram. In this problem, we have bearing stiffeners at the supports and under the concentrated loads, but no intermediate stiffeners. Thus, we have two interior web panels and two end web panels. The maximum shear in the interior and the end panel should be differentiated as tension field action can only occur in interior panels. Thus, the maximum shear for end panels is 234 kips and 102 kips for the interior panels. By observation of the moment diagram, the second and third unbraced segments have the highest bending moments. We will have a closer look at the moments in the second segment as it's the same as the third segment due to symmetry. At the first quarter of the segment, with a distance of 36 inches from the left end, we obtain moment A. At the midspan of the segment, with a distance of 72 inches from the left end, we obtain moment B. At the third quarter of the segment, with a distance of 108 inches from the left end, we obtain moment C. We start by creating a list of geometrical inputs as well as material parameters of the beam girder and stiffeners, such as the top flange yield strength, width and thickness, bottom flange yield strength, width and thickness, web yield strength, height and thickness, geometry of intermediate stiffeners if they exist or not, whether there are bearing stiffeners, their width and thickness, and whether the compression flanges are restrained or not, and if there is a double stiffener at the ends, the unbraced length of the segment in question for flexural strength, weld size between the flange and the web as well as the stiffener to web, the moments we extracted from the finite element software, the maximum shear in the end panel and in the interior panel, the concentrated load at the support, and at the internal concentrated load locations in addition to their distance from the end of the beam. After having the required inputs for evaluating the girder's structural integrity, we start by checking the dimensions and proportions of the girder and whether or not they conform to the AISC specifications. We start with the web slenderness check, where the slenderness ratio is compared to the non-compact and slender limits from AISC specifications Table B 4.1b. Next, we check the proportions for the maximum allowed web slenderness ratio as well as the maximum allowed ratio of web area to compression flange area, referring to AISC specifications Chapter F13.2. From here, we start preparing for the flexural strength calculations by finding the elastic neutral axis of the girder, the plastic neutral axis, the moment of inertia of the girder about the major axis, the elastic section modulus considering the upper and lower flange, and the plastic section modulus. We proceed to calculate the flexural strength of the girder. For flexure, the cases of tension flange yielding, compression flange yielding or buckling, and lateral torsional buckling need to be checked. The governing nominal flexural strength is then taken and multiplied by the flexural strength reduction factor, which is then compared to the maximum bending moment. If the maximum bending moment is less than the available strength, the section is sufficient for flexure. Next, the shear strength is evaluated at two locations: the end panels where tension field action does not take place, and the interior panels where tension field action can take place. We obtain from our input the maximum shear values at the end and interior panels. We can see that the shear strength at the end panel is not sufficient. Knowing the no field action shear strength equation, the strength can be increased by either increasing the shear area through increasing the web thickness, for example, or increase C sub V1 by decreasing the aspect ratio of the end panel through adding intermediate stiffeners. We will take the second approach and add intermediate stiffeners in the middle of each panel. The height of the intermediate stiffener does not extend all the way to the tension flange, but rather has a height of 61 inches. Following this adjustment, we can see that the shear strength at the end panel is now sufficient, and for the interior panels, the shear strength is also sufficient. Because we added intermediate stiffeners, their dimensions need to be checked according to the provisions of AISC specifications, section G 2.4. First condition comes from G 2.4d, the second comes from G 2.4e, and the third comes from G 2.4b. Next, we need to check the size and strength of the welds. The minimum size is checked from AISC specifications Table J 2.3, while the strength is checked using equations 8-1 from the AISC construction manual. Finally, the strength of the bearing stiffeners needs to be checked. Cases to be checked are end stiffener bearing, but please remember to account for double stiffeners at the end. Interior stiffener bearings, end stiffener and web as a compression member, interior stiffener and web as a compression member. For design of plate girders, the following steps should be made. Select the overall depth. It is recommended to start with a depth of 1/10 to 1/12 of the span. Select a trial web size. The web depth can be estimated by subtracting twice the flange thickness from the overall depth selected. The web thickness TW can then be found by using the following limitations as a guide. Then estimate the flange size. The required flange area can be estimated from a simple formula derived by assuming that compression flange buckling will control. After that, check the bending strength of the trial section. Then check shear and proportion the intermediate stiffeners to satisfy the provisions of AISC G2.3. Afterwards, design bearing stiffeners. To determine whether bearing stiffeners are needed, check the web resistance to concentrated loads for web yielding, web crippling, and web sidesway buckling. Alternatively, bearing stiffeners can be provided to fully resist the concentrated loads, and the web need not be checked. If bearing stiffeners are used, the following design procedure can be used. Try a width that brings the edge of the stiffener near the edge of the flange and a thickness that satisfies AISC equation G2-12. Then compute the cross-sectional area needed for bearing strength. Compare this area with the trial area and revise if necessary. Then check the stiffener and web assembly as a compression member. Finally, design the flange to web welds and stiffener to web welds. Don't forget to like and subscribe and turn on the notification bell. Thank you for watching.